So formal charge is one way to look at the electrons that are normally assigned to an element as valence electrons and how close that number is to the element's electrons that are the electrons that are present on an element in a molecular ion. It's basically one way to examine how stable the molecular ion that has been drawn with a Lewis diagram is with respect to the electronegativity of the atoms making up that molecular ion. So formal charge is equal to the difference between the number of valence electrons and the number of lone electrons and half of the bonding electrons assigned to an atom making up that molecular ion. So each of the oxygens here in ClO3 minus has 3 lone electron pairs and 1 bond to chlorine. So to determine the formal charge of oxygen to be -1 for each of these oxygen atoms, we would take the valence electrons present in oxygen 6, and we would take from that the 6 lone electrons, the 3 lone electron pairs, which would give us 6, and half of the electrons in the bond, 2. So 6 plus 1 would give me 7, and 6 minus 7 gives me a formal charge of -1 for all of my oxygens. With chlorine, it normally has 7 valence electrons. It only had 2 lone electrons in this molecule, and it has 6 electrons that are involved with bonds. Half of those 6 belong to chlorine, so that would be 3. 2 plus 3 is 5, and 7 minus 5 would give me a formal charge of +2. And if you add the formal charges of all of the elements making up your molecular ion, their overall charge should equal the charge of that molecule or ion. And that happens in this case, 3 minus 1 gives me -3. Add that to +2 gives me a formal charge of -1. Resonance is what occurs when you have more than one potential Lewis structure that could be written that is valid. And it happens when you have a multiple bond that can be rotated between atoms. When that occurs, the actual structure does not just share one pair of electrons, or in this case, 2 pairs of electrons more with one atom as opposed to the other. It rotates it back and forth, so it's more of an average. When you have resonance, these electrons are delocalized. They're not just going to be shared between one atom. They're going to be, or shared between 2 atoms. They're going to be shared between 3 or possibly 4 atoms. So we're going to do some formal charge examples now with the ones that we've done previously. We're going to focus just on the central atom. And when you have a stable molecule, your formal charges hopefully will be 0 or close to 0 because you want to basically have the number of valence electrons that that atom or that element normally has. You want that to be the number of electrons that that element would have assigned to it as part of that molecular ion to get its octet filled. So phosphorus normally has 5 valence electrons. All of the electrons that phosphorus has surrounding it are involved in bonds, so it has no lone electron pairs. So I would take half of those 8 electrons, 4, subtract that from 5, and that gives me a formal charge for phosphorus of +1. Now I told you you didn't only had to do the central atom, but I did want you to see where these other ones came from. Oxygen had 6 valence electrons. It has 6 lone electrons surrounding its atom and 1 pair involved with a bond. So the oxygen would have 6 minus 7, a formal charge of -1. All of the chlorines have 7 valence electrons normally. They have 6 electrons involved, 6 lone electrons assigned to them, and 1 pair involved with a bond. Apparently I didn't do chlorine, but chlorine would be 0. 7 minus 6 minus 1/2 of 2, which would give you 7 minus 7, or 0. Why is boron a moron? This formal charge example hopefully will help you see that. Boron normally has 3 valence electrons. It has 3 bonds around its atom. Because it has those 3 bonds around it, it is sharing 6 electrons with the chlorine atoms. So half of 6 would be 3, and 3 minus 3 would give you a formal charge of 0. If a lone electron pair was assigned to boron, it would have a formal charge of -2, which is definitely not as stable as 0. If it was involved with a bond in another atom, it would have a formal charge of -1. Not so great as 0, but definitely better than -2. So again, the closer you are to 0, the more stable that molecule will be. Here with C and O, it says assign the formal charge for the central atom. I'm going to lay considerable odds I did it for both since there's not really a central atom. We'll start with carbon. Carbon has 4 valence electrons. It only had 2 lone electrons on that were by itself. It had 3 pairs of electrons involved with bonds, so it had 6 bonding electrons. Half of 6 would give me 3. 3 and 2 is 5, so 4 minus 5 would give me a formal charge for carbon of -1. With oxygen, oxygen normally has 6 valence electrons. It too had 2 lone electrons and 6 electrons that were involved with bonding, so half of 6 would give me 3. 6 minus 5 would give me a formal charge of +1. -1 and +1 give you the neutral charge that we see with the C triple bonded O. We're going to draw Lewis structures for SO2 and SO3 and then show the resonance structures. We've actually already done these. I did those with y'all last week. So with SO2, you have 18 valence electrons. You're going to use up 4, connecting S to each of the O's. That leaves you with 14. You would initially put 6 around each O, which would leave you with 2 remaining, but then the sulfur that's in the center would not have a 4th pair. So that's why you had to make the multiple bond, and you can make it with either oxygen. So that is why you see the 2 different structures for SO2. You will only see resonance with molecules that obey the octet rule because they're the only ones that can have those multiple bonds. With trioxide, sulfur trioxide, you actually have 24 valence electrons able to be dispersed. You're going to use up 6 of them to bond sulfur to each of the oxygens. Sorry, I'm doing math in my head. That would leave you with 18. You will use up all 18 to take care of the oxygen atoms on the outside, but that means that sulfur would not have a 4th pair without a multiple bond. So by assigning that electron pair or sharing an electron pair with oxygen, or more than one pair, it's able to make 3 different resonance structures because there's no particular reason for it to form a double bond with any of the oxygens. It would form it with all 3. So this last piece here is going to cover bond properties and bond energies. Bond properties are going to be used to describe the characteristics of the bond. We can talk about order, which is the number of bonding electron pairs. When you have single bonds, you have a bond order of 1. When you have a double bond, you have a bond order of 2, a triple bond, a bond order of 3. If you have a resonance structure that is able to rotate a multiple bond, if it rotates it between 2 atoms, then you would be sharing it like 1.5. That would be its bond order. If it was able to share it with 3, it would have a bond order split in thirds, so 1.33. As you saw with the models, the length, the distance that we see between nuclei of 2 bonded atoms, is going to be greater with a single bond and much shorter with a triple bond. Single bonds are your longer, double in between, triple at the shorter end. And the strength of the bond is associated with its bond dissociation enthalpy. We always have to break bonds by adding energy in. You will release energy to form bonds. So breaking bond is endothermic, forming bonds is exothermic. Because triple bonds have 3 electron pairs, they're going to have a stronger bond. They're going to require more energy to break than a double bond, which has 2 pairs, or a single bond, which has 1 pair. Now, this is just an example of a chart with bond association enthalpies. We spent some time on enthalpies back with thermochem. So when we are talking about the energy that's stored in these single bonds, we're saying that you would have to absorb 436 kilojoules per mole to break a bond between these two hydrogen atoms. And if you were going to go across the chart, you can see it for H and C, H and N, H and O, H and F, etc. You are just basically reading. You won't find, you only see the tables filled in on the top half because you don't need to form the bond energy would be the same, or bond enthalpy would be the same whether I'm doing it from C to Si, C being on the y-axis, Si being on the x-axis, or if I was using Si on the y-axis and C on the x-axis. There are some that have dashes, and those I would lay considerable odds that bond association enthalpy with those molecules when they connect together is basically negligible. And so that's why those dashes are present. We talked about how single bonds are going to require the least amount of energy to break. With carbon-carbon, you see that it releases 346 kilojoules or absorbs 346 kilojoules per mole to break that bond between the two carbons. A double bond is going to almost double, 610 kilojoules. A triple bond, 835. And we see the same pattern with nitrogen, as well as the 1O double bonded O double bond O bond we see with ozone. I'm sorry, with oxygen. It's late. I'm so sorry. Listed there under multiple bonds. So this chart's there for you as a reference. If I was going to ask you a question involving this on an assessment, I would give you the bond enthalpies, or if it was part of a free response question, you would have this to be able to use. But I even think on that, I would provide you with these bond enthalpy values. Now, if this is the energy that's needed to break a bond that would have to be added to break it, this is also the amount of energy that would be released to create a bond. And so we can calculate the enthalpy of a reaction using these bond association enthalpies. Rather than doing products minus reactants, we are able to calculate delta H by looking at the net amount of energy that would be needed to break the bonds and taking away from it the amount of energy that would be released by the bonds that are being formed. So because delta H, we want to look at what energy we need to add and what energy would need to be released. We're going to kind of flip the direction that we calculate delta H in. We're not looking at products minus reactants. We're focusing on bond values. And because when you are forming bonds, it is exothermic, we need that piece to be the minus component of the enthalpy equation. So we have not focused on drawing Lewis structures before this unit, which is why I did not include this back in your enthalpy unit. I wanted you to have some practice with Lewis structures first. So use bond energy values to estimate delta H for this reaction. CH3OH and C triple bonded O form CH3COOH. And for convenience sake, I went ahead and drew the Lewis structures for you. So if we look at the reactants and products, we see that methanol, CH3OH, has 3 CH bonds, 1 C single bonded O bond, and 1 O single bonded H bond. We see that carbon monoxide has a triple bond. And then we see over here with methanoic acid, we have 3 CH bonds again. We have 1 C single bonded O bond again. We have a C single bonded C bond, an O single bonded H bond, and we also have a double bonded CO. Well, if you are going to require the same amount of energy to break bonds as the amount of energy that you're going to release to form bonds, and you have the same number of those types of bonds on both sides of the equation, you really don't have to worry about those. They kind of cancel each other out. So the CHs are going to be able to be negligible in terms of calculating delta H because they're going to both require and release the same amount of energy. The same for our C single bonded O and for our O single bonded H. So we're going to need to determine how much energy would be required to break that triple bond and how much energy would be released to form the C double bonded O and the C single bonded C. So we would use our chart to find those values. The C triple bonded O would require 1,046 kilojoules per mole of energy to break that bond, and it's 1 mole because you have a coefficient of 1 in that reaction. And then you only had one C triple bonded O there. And then on the product side, we would take away the enthalpy that would need to be released to form the C single bonded C, 346 kilojoules per mole, and the C double bonded O, 745 kilojoules per mole. Now, in all of these cases, the coefficients have had 1, and it's because when we drew out the structures, that's how many of those particular bonds we had. Notice with CH, there were 3 CH bonds. If we had kept the CHs, then you would have had 3 moles times the enthalpy that would have been needed for that CH bond. If you have a coefficient in front of one of these chemical substances in the balanced equation, you definitely need to account for it with your bonds. So if you had 2 carbon monoxides, you would have had 2 times C triple bonded O when you were examining the structures to determine what types of bonds were present. You're not required to do that part at the top where I drew out what the different bonds were so I could see what canceled. I think it helps because I think it's a way to kind of give you to track to make sure you've accounted for all the bonds, but that's up to you. The moles cancel. I would take 1046, subtract from it 346 and 745, and I get that the enthalpy for this particular reaction is negative 45 kilojoules.